Good morning friends. Today we are here in lecture on the topic of terms used in statistics, okay, or terms of statistics. This might seem very rudimentary, but until unless you understand these things, further building blocks of statistics or further buildings of statistics will not be clear. So let's go on one by one and we will go in depth and we will talk about these terms a lot, and I will be keep explaining them. Okay. So we did talk about that in our inferential statistics, that we want to know the population mean and we don't have access to that, hence we take multiple samples. Now when we take multiple samples, all samples will have a mean. Now those mean will deviate among themselves from the population mean. Okay, so that error is called the standard error. Okay, it's like standard deviation, but it's not completely standard deviation, and we will talk about an example of this also, please. Because in standard deviation, what we do, we take the units or data is sample, like 10 samples are 10 people sample is taking in one sample, 10 people are there. So we take that 10 and 10 as a denominator. We find the deviation from that mean of the 10 people and then find it. Here what we are doing, we are taking the sample mean. So if we are taking 10 samples of 5% each or 10% each or particular n, 10 different samples. Like in our figure which we drew, there were around I suppose 5 or 6 samples. Okay. Now that sample mean, there are 10 sample mean, that will give us a standard error. Okay. So a smaller the error, we understand that it is near to the population mean. Now this is very important, that if the error is smaller, as like a standard deviation, if it is small, then most of the data are near the mean. Okay, and hence if the error is small, we can say that our sample is likely a representation of the population, or our sampling distribution is replicating the population. Okay, so please understand, standard error is a very important term. This is called SE. Okay. This is not standard error of a particular sample, this is standard error of the means of the samples. So if there are m samples, each sample has n people in that, so there are m into n people. Okay, but for getting the standard error, we need m sample means of n each group, okay, n each people, and that will give us standard error. Okay, now comes a second nice concept of central limit theorem. So what the central limit theorem says, because generally we do not know that will our sample mean or our population mean will be near about or not. What it says, that if the sample is large, now particular sample, as we were talking m into n, it is not about m, it is about n, number of people in n sample. Okay, or number of units of analysis in an sample. Now what is unit of analysis? Unit of analysis, let me just touch it a little bit. Unit of analysis is, if you are studying a family, the unit of analysis is family, not 4 people or 5 people. If you are studying nation, one nation, that I am comparing one nation with second nation, the unit of analysis is nation. Okay, unit of analysis, number of n is that. Okay, then the population mean will be nearly equal to the sample mean, we can assume, and the standard deviation of the sample mean sigma is equal to s divided by root n, and root n is written by power POW, pow excel, n by n into 1 by 2, okay, n comma 1 by 2. So as n tends to infinity, you can see the sigma tends to 0. What is this sigma? This sigma is the standard error, which talks about the differences in the mean of each m samples we have taken. Okay. So if n becomes large, every sample mean will be similar to population mean. Hence, there is no standard error, and hence we are okay with it. Okay. So, sigma is equal to, sigma is the standard variation of the sampling distribution, is equal to S, which is the standard deviation of the population, divided by root n, in this case, which we are writing power n comma 1 by 2. So, central limit theory says that when the n is large, and we will see today ahead that how does this 30, the number 30 changes things. Okay. Now, there is one more term called confidence interval. So, what we said, if the standard error is low, we can say that the sampling mean is, sample mean or distribution, sample distribution mean is nearly to the population mean. We can say that. Okay. But how much percentage and those sort of things were a bit difficult. Okay. So, therefore, we also have one more parameter called confidence interval. Okay. This gives a boundary by which we are confident, okay, that we will have the population mean in this range. Okay. Now, this is not confidence level per se, this is confidence interval. Please understand, we will go and find it at confidence level and confidence interval are different thing. Okay. So, it is a boundary, okay, in which we are likely to find the population mean. Okay. Now, let us take an example. So, if you see an image downstairs, okay, this is taken from Andy Field, chapter 2, this is figure 2.1, 2.8, yeah, okay. So, this is very important. What it says is, let us not go into the detail of the experiment right now too much. So, they are trying to understand and they have taken multiple samples. Now, as they have taken multiple samples, we also know that the samples themselves will be varying between one limit to another limit. Okay. So, this is denoted by and I. So, this is an horizontal I with mean being the at between of the I. Okay. So, now please understand, not let me read that. So, when we see 95% confidence interval for a mean, it means that we would collect 100 samples from the population, and out of that 95 times we will find the population mean in the I range. And as you can see, the arrows which we are here talking about does not contain the population mean. Okay. The first arrow, the sample is too low, below the population mean, and the second and third, it is quite ahead, or it is more than that. Okay. So, this is for 50 samples. Okay. So, like in this 50 samples, 3 times we are not finding the mean in the range of the I. Okay. What is the I? Interval of the interval of the sample mean, particular sample mean. So, this is called confidence interval. Now, this is a very mathematical term, and this will be repeated again and again, and we will talk about it much more. Okay. So, how do we get it? Now, x bar is the sample mean of the distribution for all the samples. Okay. Now, sigma alpha by 2, why it is alpha by 2? Now, let me take you to the I think slides where we did find the probability area. It was two-tailed, okay, tail on both sides. Let's take it there. Let's take with the pen, no problem. So, if I am saying this is 95%, okay, then this has to be 2.5% and this has to be 2.5%, and therefore, the term z alpha by 2 is used there. So, alpha, as we talked about earlier, alpha is the amount of error we will tolerate in our samples, okay, in our sampling. So, alpha generally is 5%. So, alpha by 2 is 2.5%. Okay. So, therefore, it is Z alpha by 2. Now, if you remember the formula, x is equal to Z is equal to x minus mu by sigma. Now, sigma in this case is, as you can see, we have written. Now, please understand, the notation of S and sigma are interchangeably used. This sigma is the population mean again. Okay, this is not the sample mean. Please understand. Okay, so this sigma can be written by S by root n. Okay. So that you can see, that is why S by root n is there. Now, we have two Z's, one here and one here, and therefore, we get two ranges, okay, two values within which the mu will lie. Mu, what is mu? As we generally talked, mu is the population mean and x bar is the sample mean. Okay. So, if you take a particular sample, and we will talk about it later also, if you take a particular sample, it has an x bar and standard deviation is given, okay, and we can calculate. Now, okay, again it is same thing but written in different way, please understand. We need to know the limits at which 95% of means will fall. So, what is lower average? 1.96 into standard error. Why 1.96? Let us go to the Z table, let us see if we have the link of that. Yeah, this one I was talking about. So, we are looking for this sort of plot, okay, or precisely this sort of plot. So, when we put x is equal to 1.96, what do we get? From minus 1.96 to plus 1.96, this sort of calculation comes, we get 95%. Therefore, we have put 1.96. Okay. If you just write this way, this will be 0.975. Okay. So, we are looking for this. So, 1.96 Z from minus 1.96 to Z plus 1.96, we have 95%, and as we remember, we discussed in the normal graph, between minus 1 sigma to plus 1 sigma, we have 68% of data. Okay. That is what we are talking about here. In that way, things are building up. Okay. So, now going back, hence we have 1.96. 1.96 is Z alpha by 2, where alpha is 5. Now, please understand, this is for 1.96 or 95%. If you want 90%, you have to take different values. Okay. We know that 95% of confidence intervals contain the true mean, so we can assume this confidence interval can contains the true mean. So, population mean is also called the true mean. Okay. Therefore, if the interval is small, the sample mean must be very close to the true mean. Okay. And conversely, if the confidence interval is very wide, the sample mean could be very different from the true mean. Now, please understand, let us see, if our alpha decreases like increases, like we say 5% error, now we say it is let us say 2%, okay, from 5% to 2%. So, what will happen? We have to capture 98% of this portion in the pink region, and hence our Zx will increase. So, let us try 1.99. Okay, no, not this one. I don't know how much when you get in 2.4, 2.6, 3, yeah, 2.6, 2.4, yeah, something like this. So you can say 2.3. Okay, so z is equal to 2.3 minus 2.32 plus 2.3 will be our error, okay, for the z. Okay. Now what it will do? It will increase the confidence level. So that is what it means. Okay. Again, it does it what it means, if we draw sample 100 times, okay, the population mean will fall in the range of 95% of the samples, as we did in our case. Okay. Confidence interval for a mean is a range of scores constructed such that population will lie within this 95% of sample time. So if you take 100 sample in this range, the population mean will lie. Please understand, confidence interval is a range. We are never sure, like if we have small SE, we can have small interval, but still it's an interval. Okay, small SE means either it on the right side or left side, we don't know, so it's a range again. Okay, small SE is required, that's fine, that's good, but we can never form the true mean. We can just find the range of the true mean and we can make it narrow. That's all we can do. Okay, please understand that. Okay, these three terms are again very important. So we have discussed what is a standard error, we have discussed what is confidence interval. Okay, now what we are discussing are three different terms: statistics, a parameter, and an estimate. Okay. So please understand, a parameter is for the population, though they are, what happens, like we have word called hot and warm and people mix them, this is warm, this is hot. So similarly, unfortunately, terms parameter, estimate and statistics are interchangeably used. Unfortunately, that's the thing. However, if you go by books and if you go by statistical research, parameter is about the population. Okay, so population mean, population median, population standard deviation, population frequency, everything about the population, that is parameter. Parameter, P for population, P for parameter. Okay, though they have parameter different definition also, what are the parameters for you to make decisions, that is a different decision making science, but when we say parameter of a population is this. Okay, now a statistic is generally description of a sample. Generally, I am not saying always, generally, because as we talked generally later or previously also, it is very difficult to do a census. If you do census, the statistic becomes the data of the census. So particular point value will become like mean, median, standard deviation, and these are generally about the sample. Okay. Now, estimate is something which is trying to estimate the parameter, because as we say, the parameter is what we are interested in. Okay, we don't know what the parameter is. So an estimate is a single approximation, like this much could be there. So using statistic, we try to get an estimate thinking it is near to the parameter. Okay, so we have internal estimate, that is what we have discussed. Okay, that is internal estimate. Okay, estimate this much is the interval in which we think the parameter will lie, the parameter of population mean. Please don't think only population mean can be a parameter, there can be multiple parameter. Most likely we will be discussing only population mean, but we can discuss other things also like median, mode, or maybe also your standard deviation, variance. Okay, and there are tests for that. We will not be doing it, but for your information, parameters is not only mean. Okay, and prediction also. So estimate. So therefore you will hear this term, the estimate of the function, the estimate of the regression model is this. We have estimated the value to be this. We have estimated means we have by calculation, this is the value which is coming up. Okay, so statistic, parameter and estimate, these are three different things. Going ahead, this is also very, very important. we will be hearing about the word explained variance, unexplained variance. Variance. So what happens, please understand this, let me not get into ANOVA, we will get into this into more in detail in ANOVA, that what happens, there is a variation in the data which is given to us. Okay, what is the variation? The variation is in the dependent variable. Variation is not talked about as the independent variable. Variation is talked about the independent variable y. So there is a variation in the y. Now, if our predicted model is variation is equivalent to the variation of the observed variation, then we say we have explained 100% of the variation by using our model. Okay, it's simple. Like if you're trying to, आपको समझाने की कोशिश कर रहे हैं, ये पूरी समझ है, ये इतना समझ में आया और इतना समझ में नहीं आया, और ये पूरा समझ है. So जितना समझ में आया और जितना समझ में नहीं आया. So that is what is variance explained and unexplained variance. Now this variant explained is known by multiple synonyms in literature: model variance, treatment variance, regulated variance, deterministic variance. Okay, and unexplained variance is also called residual variance, error variance, random variance, noise variance. Because you understand, when you explain the treatment, let me go by the medical terms. Okay, so let's say we were talking about somebody's platelet counts and we want it to change, and we found it has changed, let's say 20%. Now our medicine, because the person is not just taking medicine, person is also doing exercise, person is also taking some other things, might be taking alternative medicine or some therapies or other things. Okay, so now to say this, that the medicine is completely responsible for the 20% platelets change will be too much of a claim, though it is possible, but generally it is not. So a good medicine is that which can at least increase it by 60-17%, and it might be possible that the person has increased his platelets by 3% himself, or could be other way around. The medicine could have increased the platelets by 23%, and he himself by other things has decreased it. Okay, so therefore please understand, total variance will be, and we are talking variance, okay, not deviations. So total variance is equal to explained variance or variance which is explainable, which in our medical case was the treatment. The variance is due to this particular treatment. Please understand this example, very important. If I am losing my weight 5 kgs, how much of those 5 kgs are reduced due to my going to gym, and how much of that is reduced my change in diet or my taking other physical steps? That is very important. So if I have lost 5 kgs, I can say that 4% of the weight has been lost to training and 1 kg has been lost to other things. This other thing is called noise, because we don't know what is that. It's noise. What is noise? Signal which we cannot understand. Those who know electronics, signal to noise ratio. What is noise? Like sometimes the humming voice comes in when I'm not talking, and sometimes the humming noise will come and magnify. That is called noise. Noise going into the signal. So noise is which we don't understand. Actually, it's a very simple thing. If there are people speaking, let's say Tamil here, for me it's noise. I don't understand Tamil. But for people who understand Tamil, that is not noise, that is signal, or that is treatment. Okay. So noise is which we are, therefore I use the word unexplained. Other people will use random and residual and error. I have no issues, but I'm trying to say it is unexplained by us yet till now. Okay, and this is a very conceptual topic to differentiate what is explainable, what is unexplainable. Okay, so this is the total variance is always explained variance and unexplained variance. Simple. Explained variance is known by these synonyms, and unexplained variance is known by these synonyms. Now, there is one more term called degrees of freedom, which we have to understand. Now, let me recheck it. This has become a little problematic. So, when you read statistics books, you will find a term called DF. Now, what is DF? DF is degree of freedom. What does freedom means and what is the degree of freedom? Okay. Let's talk about equation x plus y equal to 4. Okay. I am drawing down the pad. Here again, x plus y equal to 1. Now, can I say both x and y are independent simultaneously? No, because if x is 2, y cannot be anything, y has to be minus 1. If x is 4, y has to be minus 3, or y is dependent on x. Okay? Y is dependent on x, so only one independent variable is there, IV. Similarly, the equation I have written, z is equal to 3 minus x plus y. So, if we write this equation, z plus x plus y, only this. Let me remove all the. Now, here also, if you can see, if x is 1, y can be something. Let us say y is 0. Then z cannot be anything. Z has to be 2. So, now here only 2 variables are independent. As I wrote, x is equal to 3 minus z minus y or otherwise. Okay, that's why I written. Let's check. Okay, or z is equal to 3 minus x minus y. So, when you have only one equation, you have 2 and 3 variables. You have 2 different degrees of freedom, both x and y, or y and z, or x and z. That's different thing, but only 2 variables can change. Okay, let's come to a system of equations. Suppose we have 2 equations, x plus y plus z is equal to 3 and x plus y minus z is equal to 4. Now, as you can see, both of these equations have, if we go by previous logic, two different variables, but because there are 2 equations, in earlier cases we have 3 variable 1 equation, now we have 3 variable 2 equations. Okay. So, we have an equation when we combine this, x plus y is equal to 3.5, which means only one variable is free. Therefore, in books you will find this formula df is equal to n minus 1 minus k. N minus 1 you will find everywhere, and you will read n minus 1 someplace, because at that place equation is only 1. There is only one equation. Okay. So, df is equal to n minus k. Okay, where n is number of variables, k is number of equation, and in our case, as we had z is equal to 3 minus x minus y, if only one equation, k is 1, n is 2, so degree of freedom is, n is 3, the degree of freedom is 2. Okay. So, n minus k is the degree of freedom, where k is number of distinct equations, please understand. Like, what does it mean, distinct equation? If I write x plus y is equal to 4 and 2x plus 2y is equal to 8. You might say these are 2 equations. No, there are only one equation, because this is ultimately x plus y is equal to 4. Okay. So, x plus y is equal to 4, number of different or distinct equations, not different but distinct. Okay. So, df is equal to n minus k. Okay. So, now there is something called a student T test. We will talk about these things separately, differently, do not worry about that. So, what is a student T test? Okay. This is what we have seen, but if you remember, we have seen here T is equal to Z. Mathematically, the function, the value of t is this, where there is a gamma function and there is a beta function, okay, and v is number of degree of freedom. Now, if, as I told you, if you remember central limit theorem, the central limit theorem thing when n is large, and we were saying that we will talk about how this 30 number came up. But when n is small, then we apply student t test. Okay. Now, this is the value of the t statistic, x bar minus mu s by root n, and the degree of freedom is n minus 1, where n minus is the unit. So, why n minus 1? Because there are n values. Okay. So, if 1 plus 2 plus 3 is equal to x average, okay, x average into 3, then it is an equation. So, only 2 variables are free. So, 3 minus 1 is 2, and therefore, n minus 1 number of variables, number of different entities minus 1, that is degree of freedom. Okay. Similarly, the confidence interval is like this. Here also we will show you what is the t test table, don't worry. Okay. So, x minus same thing, confidence interval is similar as that. Please you understand, here we are not writing z, here we are writing x. Z is only for n more than 30, for n less than 30 we write t. Okay. Now, as you can see, v is a degree of freedom, you can see where I am putting 1, 1, 2, 5. So, as the degree of freedom increases to 30, it reaches as a distribution of normal curve. Okay. This is again one more understanding, please see. The blue line on the top figure is the normal curve. Okay. Degree 1, then degree 2, and then degree 3. As you can see, as the degree is increasing, it will approach to normal. Okay. So, in this way, these are showing us the t distribution approaches a normal curve when n is more than 30. Okay. When n is less than 30, we use it differently. Okay.